If you are new to the channel, then subscribe the channel and press the bell icon for further notification. Okay, student, welcome you all to this new lecture in machine series. So today again we will be solving 5 questions starting from question number 141 to question number 145. Okay, then let's try to solve these questions. Okay, in question number 141, what is asked? In a variable frequency induction motor drive, the voltage must be varied dash to the frequency. So induction motor is like your transformer, but in transformer it cannot rotate. Induction motor, there is a possibility of rotation because the rotor is free to rotate. So what happens is there, because transformer is also constant flux, so rotor, your induction motor is also a constant flux machine. So because it's flux, to make it constant, if you see its EMF, that is also same 4.44, that phi f, that formula. So here also phi is directly proportional to E by F. So in induction motor, your speed that is equal to 120 F by P and S, that can be controlled by changing B. So whenever you F by changing F. So whenever you change F, there is a chance of changing this phi, which will change again this equation E and all other things. So generally it is kept constant, that is phi. Like your transformer, I told you it is a mostly like a constant flux machine. So because it is, to make it constant, if you are changing in flux, that means accordingly you have to change in E. So that's why it is always V by F, this ratio is always kept constant. So this is always maintained. So if you are change this one, accordingly you have to change this one. So this is a linear relation. If you are increasing this one, this should also increase. If you are decreasing this one, that should also decrease, because E and F, you can see there is a linear relation. So it should be varied linearly. Now if you come to question number 142, an induction motor is fed from a balanced 3-phase supply at rated voltage and frequency through a bank of 3 single-phase transformers connected to delta delta. 1 unit of the bank developed faults and is removed. Then, so I think we have discussed this type of questions in question number 69. You can check this one in transformer. But there, because in that case it was directly one phase was disconnected, so we started with that open delta only. So we started, we have seen the power is equal to 3 into your kVA rating divided by root 3. So that is for open delta. Now if you see, you have a delta connection like that, 3-phase. So here it is root 3. I know what is the power, root 3 VL IL. And in case of delta, this phase, I phase, if I write it in terms of I phase, so it will be root 3 VL. And what is IL? IL is equal to root 3 into IP. So it is actually 3 VL IP in delta, because VL equal to VP. So it becomes in this one. Now if it is an open delta, suppose you have of this fashion. Now whatever the line current, that becomes your phase current. You can see your line current is your phase current, your line current is your phase current. So here it is root 3 into VLIL, and IL is simply IP here. So if you, this is delta and this is open delta, you can say. So it is root 3 VLIP. So what is the change here? What is the rating now? How the rating is changed? So it is how much percentage of this one? You can see open delta divided by original delta. Open delta is root 3 VL I phase. This is root 3 VL I phase. So it is actually 1 by root 3, which is 57.7%. So it is not actually 2/3 of this one. So this is actually 57.7%. And in that questions we have already solved this one. That is was total was, I guess it was 15 into 15. Whatever in normal delta, but suppose it is of X rating, one single phase. So in normal delta it will be, total rating will be 3 into X. And in open delta it will be 57.7% of this one. So what is it is saying, that one phase if it gone, we know that single phase will not occur. It will be 2 phase. 2 phase will also serve the purpose, because it will also work like a polyphase. In polyphase there will be a rotating magnetic field. So for induction motor you need this one. So single phasing will not occur, so that is sure. But the motor terminal voltage will become unbalanced. It is not unbalanced. All the 3 phases are present. So accordingly, your motor will get power. So motor will get power from three phases. So the voltages will be balanced because all 3 phases are present. So this unbalanced voltage will not occur. The machine will be loaded to the extent of 57.7, but that is okay, because your rating will reduce now of this rating with balanced supply at its terminal. So that is option A, C. So if you come to question number 143, what is asked here? An induction motor runs under stable condition with a constant torque load at 1250 RPM of a 50 Hz supply, the number of poles. Okay, you see your RPM, you see your Hertz. So if you calculate your NS, 120 F by P. So 120 into F is given 15. Now you don't know P. You start with P, suppose 2. If your P is 2, then this will be 3000 RPM. So its speed should be somewhat less than 3000 RPM, but it is very much less than 3000. It is not. Your sleep is generally 2 to 4%. So if your pole is now, let me take 120 amp by pole is, next pair is 4. So if you go to 4, then it is 30, then it is 1500. And if you go to 6, next pole pair 6, it is 1000. So obviously it is not less than 1000, it is less than 1500. If you take 1000, then it is more than 1000, then it will not be a motor, it will be a generator. So obviously you will go for this one, 1500 RPM NS. So that's why your speed is little less than that one. That means your number of poles you have taken 4. So 4 is your answer. Next, if you come to question number 144, when started by means of an auto transformer with 50% tapping, the supply current at the start of the induction motor is reduced to that of started by means of star delta starter. Now I am not going to explain that starter, but I think you know all these formulas. If I am using auto transformer, then I auto will be equal to how much it is reduced, because you are reading 50% tapping, so it is 0.5 square of your starting current. Whatever starting current it is supposed to take, now it will take 0.5 square. You can remember it in this way, because auto transformer you can think it in this way, because you are changing the tap positions. So but your total power remains same, so it is I square R. So you can remember from there I square R, but actual derivations I am not doing. So in case of star delta starter, so it is actually because you are changing your voltage from phase to line, so there is a factor of √3, so it becomes 1 by √3 of your starting current. So starting current reduced by 1 by √3 times. Now they are asking the supply current at the start of the induction motor is reduced to that of 1. So how much it is reduced? It is reduced this much on this much when started by means of, if it start with this one, then this much will current, but it is starting with this one. So how much it is reduced? 0.5 square into IST divided by ISC into 1 by √3. So it is actually √3 into 0.5 square. So you can see it is 0.433 times. So that is your answer. Next you come to 145. Unbalanced supply given to a 3-phase delta connected induction motor will cause, because it is delta connected, in case of unbalance your negative sequence and zero sequence there will come. So obviously because it is delta, there is no positions of zero sequence that has to flow through ground. So less it is in the code, so negative sequence current component, obviously because it is unbalanced negative sequence, and all will not be occur because zero sequence is not coming here. So obviously it will be negative sequence component current. That is your option C. If you like the video, then press the like button and please give your valuable comments in the comment section.